Hello, I am Guillermo Varela from Magni Europe, and I'm here today with Jesus Marini from Moonrabbit Adaptive Lab. Jesus is the founder and computational design engineer and at Moonrabbit. He's a design engineer specialized in data-driven computational design workflows and the advancement of computer-aided engineering applications. He focuses on performance sports, fashions, and biomechanics. The webinar will address the importance of multidisciplinary collaboration in building strong teams of computational design, and it will explore how diverse skills and perspectives drive innovation and lead to robust design solutions. Remember that in the last 15 minutes of this webinar, we will have some time for Q&A, so you can ask questions in the chat, and we will check them at the end. Also, I'd like to mention that the webinar is being recorded and will be available on our YouTube channel, where you can find more webinars and tutorials. Probably will upload it tomorrow. And that's all from my side. Thank you again, Jesus, for accepting the invitation. And please start with the presentation if you're ready.
Thank you, Guillermo. Thank you for the opportunity, and let's start.
You're welcome.
So, okay, let me move this so you can see well the presentation.
Yes,
So,
perfect.
hello, everyone. Thank you for joining today. Today, we will talk about how to unleash the power of computational design. My name is Jesus Marine. I'm the founder and computational design engineer at Moonrabbit Adaptive Lab. Today, we will be talking about different steps. I wanted to spend a little bit of time explaining how come I arrived in the world of computational design, what is Moonrabbit, and what do we do, and why computational design is getting important, and why we are using it in terms of our product design process. And then we will explain two showcases in which we use different approaches of computational design tools, computational design approach, so we can explain better and trying to showcase two different methods that we use. So as Guillermo said, my background comes from mechatronic engineering. I studied in Mexico, the bachelor's, and then I did a master's in design engineering at Politecnico de Milano, where I'm currently am, and the studio is based. Also from academic background, I did two exchanges. One was in collaboration with Stanford University that I did the program IM310. And the second one was a visiting student at MIT Design Lab in Boston. So my path to computational design was a little bit wavy. I have to say that I never had like a standard way to go, like a linear path. So I started from the CAE engineering. I specialized in crash impact structural analysis, and I started working in Ford. Then suddenly started moving around different areas. I did interaction design, I did digital fashion, I did product design in a little bit more of traditional way. And finally, I moved into a more research and freelance design engineering. So I didn't know how let's say that I move into different areas in order to try to map better what I wanted. So at the end, in 2022, I helped also Samsung in creating the pilot project of the first computational design lab. I've been working with a lot of different companies, a lot of different studios and people. So finally, I decided to create Moonrabbit Adaptive Lab. What is Moonrabbit Adaptive Lab? So we are an Italian startup that we've been launching as a company in 2023, and we are made by a multidisciplinary and a multicultural team specializing in computational design for consumer products. So something that we want to specialize, or we are specializing, is how to bring these techniques into product design, which is something that I think really interesting, because now that we are having more data, more process, more approaches, it's easier to adapt into our design processes. So to unleash the potential of emerging technologies, this is our mission, by creating a bridge between the new and the traditional development processes. These are the areas that we merge. we are trying to expand in different fields, especially in the part of design, the part of engineering. We specialize in material science and computer science. That's why we are creating a team that is formed by different disciplines. We are M-shaped, T-shaped designers, engineers that also we are trying to combine our strategies, combine our skills in order to create a good approach for the projects that we are doing. Recently, in this last couple of months, we've been in different places. We've been around Milano Design Week, Genova Design Week. We participated in Vision Date also here at Milan. We've been in CDFM in Berlin. We've been mentioned also in a museum besides other magazines. So we are keeping also our events, our research, and our communication. We have four main focus sectors. Performance, computational design, simulations, and design for additive manufacturing. The part of performance, what we do is we apply engineering. We create data collection, data analytics, and process automatization. So one of our specialization is how to utilize data, transform it, collect it, modify it, and create processes that enhance the performance of products. In computational design modeling, we create parametric modeling, generative models in order to create custom algorithms that can enhance the use, texturing, optimization, data-driven solution, etc. in our product design. One of the main expertise that we have inside the studio is the use of simulations. So we are trying to combine the part of explicit simulations, dynamic simulations, trying to go more in depth about this part of the engineering, in which we can understand better the material, better the process, better the progress, try to understand the tools that we are using, why these tools are being used in that way, and how can we apply it into different fields of applications. And finally, we believe that design for additive manufacturing is an important part of our workflow. So that's why we are focusing on how to combine everything at the same time. We are seeing this work stream that goes directly with additive manufacturing. So we are specializing in how to create lattice structures, how to create algorithms for customization, for automatization, specializes for different processes in the field of additive manufacturing. So why we decide to go and specialize in computational design? Design is rapidly evolving, and we know that process and problems are becoming more complex each day. So we need different approaches to solve those problems. In order to do that, we are building a cross-functional team because we need to highlight different areas of expertise. It's not easy to just be vertical in one direction, trying to specialize and know one. We need to understand what is outside, let's say, our main path. So we need to understand engineering, we need to understand design, we need to understand new technologies, we need to understand manufacturing and combine it together. It's not easy that one single person has all these characteristics. So we're trying to create a team that can understand different parts of it. So that's why we are trying to specialize in computational design, which is really interesting because computational design excels in breaking down complex systems. So we are starting to think about how to create computational thinking, how to create algorithms, how to create processes that can connect all of these fields. So how can we create algorithms that enhance efficiency, that enhance scalability, adaptability, in order to solve all these kind of complicated problems? So computational design is something that we find like the umbrella of a lot of fields of expertise. So in order to do that, we want to explain it by two case studies. The first case studies was a project that we did in collaboration with ETH. Thanks to Thomas Bochner, that is a PhD candidate. He wanted to develop a soft robotic hand in order to prove Inkbit technology with BCJ technology. It was a new way of 3D printing. So Inkbit along with ETH, we're developing a technology of multi-material additive manufacturing. So how come can we solve this complex problem? So Inkbit has the ability to print with different type of stiffness, different type of material, different type of shores. So how can we use these materials to produce something in one single shot, in one single print, that actually can be like just taken out of the printer and putting the sensors, putting the cables, creating the motors, and then ready to go. So in order to do that, we needed to understand how to build the system, how to build the hand. So we started from an MRI, created the point cloud, creating the mesh model. Once that we have the mesh model, we started to identify what are the biomechanical elements, what are the important parts and the important sections that we needed in order to create like a full system that was able to be printed in one single shot. So we identify the bones, the ligaments structure, the interfaces 50-50. The 50-50 interface were the parts in which the joints were changing from a rigid material into a soft material. So besides all of this, we need to understand also all the characteristics of design for additive manufacturing. So what are how the boundary needs to be, what are the minimum thickness, how the process need to come, how they need to take the wax out, because in order to use support they use wax. No, they don't use like normal supports like in FDM or powder, so they use wax as support. So we need to understand all of these complex kind of constraints, boundaries, movements, and put it all together inside a product, in this case a hand. So our first approach was basically, okay, let's take Rhino, let's use the base model, let's start creating everything by hand, little by little. So we start creating the capsules, the ligaments, the joints, we created the tubes, we created the pulleys and everything together. We kind of spent a lot of time making of this, and once that we have one prototype, we send it to print and said, okay, no, you need to change this, you need to change that. And at that moment, we actually realized that if we wanted to change maybe one tube, one pipe, we need to change everything. Everything was interlocked or was dependent to anything. So for example, if we wanted to change the tube, we need to change the capsule because there was an interception and it was not possible to have an interception. We needed to have like some spacing, some boundaries. So this problem become complex really fast. So one of our thoughts was, okay, how can we use smart systems, for example, like optimization algorithms in order to create the base elements? So we know that the bones are the base element. So the next base element was the capsules, because those capsules were like the base for everything else in order to create the intersections, in order to create the joint, the interface 50-50, etc. So something that we wanted to create or to improve was how can we actually utilize, how can we base our design using the joint capsules. So we identified that this is the first part that we identified. And after that, we start creating all the elements around. So we understand that the 50-50 interface between the rigid and the soft material. We identify how to create the pipes. We create an algorithm in order to avoid collisions. So once that we identified the base elements, it was super easy to create the following parts. And then once that we created the basic shapes, we could also create all the custom components. For example, we could create all the joints 50-50 materials. We could create the interfaces between them, the holes for draining. We could create the ligaments. We can actually use everything. Something that we also said that we don't need to do everything parametric, right? At the end, we just need to use parametric design, parametric model in a way that actually solves that problem. Besides that, we have a lot of manual work. So this is also important to identify when to use parametric modeling and when to use like normal or traditional systems. So After 8 iterations, we achieved the final result. So basically, we created a full algorithm that was using the Galapagos the Galapagos plugin in order to generate the joint capsules adapted ones that we wanted to move the bonds and everything. So it was adapting to each other. One that was adapting to each other, we were creating the 50-50 interface and so on. So once that we have something that actually was working, that was good with clearance, with parameters, with everything, we did manually the draining course and the sensor paths. Something that was missing at that moment, because this was a project developed in 2021, was what if we can push further the boundaries of computational design? So now that we have different type of technologies, we thought, okay, let's try to use intact solution like meshless simulation. At the time, we were not had the capacity or the capabilities to actually simulate these kind of problems, because we didn't have anything that was able to simulate such a complex environment. So in this case, today we have some things or some tools that actually can help us to identify and simulate multi-materials inside the simulation. So, for example, today we could identify the ligaments, we can identify if something has a lot of stress, a lot of strain, if we need to modify the intersections, maybe if it's going to pull, if it's going to bend, it's going to break. So we have a little bit more of a clear idea in order to create informed designs. This is the process of BCJ printing of Inkbit, that actually what they do is taking everything, creating PNG files, and then they put like a bitmap. So basically the materials, the interface, the rigid materials of material 50% wax, everything was identified by a bitmap. So you create layers of PNGs and then you print it, which I think is really, really interesting, because this one also could be an evolution in the future of about multi-material additive manufacturing lab. How can we control these systems in order to create different approaches and different kind of intersections between materials, or how can we program them to do what we want to do? At the end, this was the result. After Thomas, I mean, we only did the design. Thomas did all the part of creating the sensor, adding the part of the actuators and instrumentation and so on. But in terms of design, we realized that actually the technology is a little bit behind of what what was needed in order to produce a multi-material object. So we needed to create a lot of tools. We needed to create a specific system in order to be able to achieve something of this complexity. So something that we realized is like tools, they need to improve. We need to push further the development of such tools in order to be able to also use these amazing technologies. Then we have the second case study that we developed in collaboration with PUMA. Then we go to the other extreme of our human body. Now we go to the foot. And we try to we collaborate with the PUMA Innovation, PUMA Nitro Lab, and we develop a project specifically for Karsten Warlhom in collaboration with Coach Leaf. So this project was, how can we use computational designs in order to create performance footwear? So it was a big question. Actually, it was really interesting how the approach was taken in order to develop a specific section of this tooling, of this footwear component. So we focus in how can we improve the toe part. So it's the ending part of the footwear. So can we improve like the performance? How can we add features, for example, the claw feature that Karsten is using and so on. So this was a really challenging approach. So in order to do that, we start thinking, okay, we know the project brief. We know what we need to get in between. So we map a process. So we start on creating, like, for example, what do we need in order to arrive to a final computational design object or product that is capable of meeting these performance requirements. So we start identifying what are the data elements, how can we get those data elements, how can we transform those data elements into digital assets, how can we visualize the information of those digital assets, how can we create virtual comparisons in order to identify what's the best product, the best performance of the infinite possibilities that we can have. And then we of course, we need to go into a design process optimization, evaluation, and prototyping. So in order to do all of this, once that we map everything that we need to do, we needed to create a lot of tools. And this was the hardest part, let's say, like of each one of these processes. We created a lot of tools. So for example, this is just like a big screenshot of one of the scripts that we did. Actually, this script is really, it's not only like a spaghetti monster. It has a lot of clusters. It has a lot of data processing. We use hubs. We use Galapagos in order to create shape form algorithms and so on. So we needed to create tools in order to be able to solve such a complicated problem. So how can we utilize data, transform the data, visualize the data, simulate the data, and then put it again into the product? So this is just a small script snapshot that we did for visualizing the data, the biomechanical data. So actually we can map the data directly into the product. We can map the biomechanical performance. For this, we create a lot of scripts, algorithms, proprietary of our own, in order to understand what the information that we needed to do, how can we visualize it, what's the best way to show it. This was before Rhino 8, so we use hubs. So now, thanks to Rhino 8, we can use it directly with Python. And yeah, we can use Python 3 directly on Rhino 8. So a lot of this was already kind of merged. So in this way, we can also visualize the data directly on the 3D model. So I think this is something important to identify. Like, we have data, but what we do with this data? So how can we actually take advantage of the information, and how can we put it in a place that actually we can inform our designs? Going back, we need to get the data. So we started by creating experimental data collection, thanks to the PUMA Innovation team, thanks to the PUMA Nitro team. We use this information in order to create these algorithms that we show. So we try to cluster, compress, analyze, utilize all this information in a way that actually was making sense for our purposes. And then we identify what are the parameters or the materials inside this performance element. So something that is really interesting and at the same time a little bit complicated is that the materials that we are seeing are in different range of stiffness, different range of compositions. We have carbon plates, we have mid-source of foams, we have power plates of different kind of plastic models. We have titanium spikes, we have the track surface. So everything was different materials. So we needed to create different approaches in terms of engineering. We did material characterization. We studied the different ways of how can we simulate each one of these elements in the best way possible. How can we characterize the materials? And that's why we needed to create also engineering models in order to do FEA simulations. So something that was also really interesting is how can we merge all of these different approaches? How can we merge engineering, CAD modeling, mesh modeling, in order to pull something like this? At the end, we achieved the creation of a high-speed simulations with large information and high loads. So what you're seeing here is the combination of all this information plus in an FEA analysis capable of identify each component stress, each component strain, identify the characteristics of all of these parts. So once that we have this information, we validate it, and at the same time, we use these simulation results in order to inform our new design decisions. So for example, in this case, we need to take back the information of the simulation and redesign the closed system or the closed part. So what we did is, okay, let's take new data, let's create new tools, let's try to identify how can we optimize the toe section, what do we need, plantar distribution, stress, spike position angles, etc. Put it everything into a mixer and identifying the main characteristics. And at the end, we also do a verification in order to see if the performance is meeting the requirements that we're doing. So in these simulations, we can actually try a lot of different physical samples. So for example, we can change the material, we can change the performance, we can change also the biomechanical information and so on in order to identify possible problems. What is the best combination of material? And of course, it's always important to do model validation because these ones are just virtual simulations that can be close to reality in a certain degree because your input quality will actually guide your output quality. So if you have good data, you will have good output. So that's also important to know. And these kind of simulations, they require quite of expertise in order to arrive to this degree of detail. Finally, something that we like to show, but we know that is mostly the athlete doing this kind of the performance. It goes completely to the athlete. We just do like a little part of the improvement. It was that he won the world championship in 2023 with the Nike shoe. So even if the athlete makes most of the work, I'm sure that we could have helped in the 0.001% or 0.001 second in order to help him to achieve his goal. So far, this is our presentation, and thank you so much for the opportunity. And please, if you have any questions, I will be happy to answer them. And let's see if I can answer all the questions. And let's try. Thank you.
Thanks, Jesus. Yes, it has been great. I have seen this project already a month ago, maybe, but it's great to see them again and with a bit more time. We had a question about the muscles in the hand, that you don't have muscles, and Aaron Porphy was explaining that the tendons act as a muscle, right?
Yeah, we have the tendons, and that's the part. Something that we identify is that we need in the hand the elements that, for example, when you are bending in this direction, it doesn't go like sideways and so on. So we identify what are the components that actually you need to use or to add in order to create the correct performance of the closing hands. So the muscles, what they do is trying to support the rest, but that's why also we use the combinations of the materials in order to kind of support the hand performance.
Yes, exactly. I'm checking if there are more questions. Yeah, Robert Falconer is asking, how was the shoe prototype? How were the results fed back into your scripts?
Well, the shoe was prototyped directly, I mean, by PUMA. So they created the shoe. We reanalyzed the data. We use high-speed videos in order to analyze the performance, the degree of deformation, and then we feed back the information into our simulations in order to see the results. I mean, in results in terms of deformation. And once that we have this, we created a script in order to pull the data out of the simulation and then inform it directly into the CAD modeling again.
Okay, thank you. And David Ramirez is asking, do you use only Rhino to create the FEA analysis, and what plugins do you recommend to learn?
Well, we use Rhino to create the FEA analysis. We created our own scripts in order to create the meshes. So actually what we did was to identify what is the API, what are the requirements in the card. I mean, if you are familiar with FEA analysis, you know that the deck card So you know how the data is kind of made. So you need to create the scripts that represent the data of the decks that you're using. If you're using Abacus, LSDyna, OpenRadios, etc., you need to use that information in order to create your own way of setting those data. And yeah, we try to use, for example, the APIs of the software that we were using for simulations in synergy with Rhino and Grasshopper.
Thanks. Yes, I will check the next question from Gabriele was again about the plugins for FEA. So that's
Yeah,
already answered.
we develop our own clusters, our own plugins, APIs. So basically, this is something that we saw that is lacking. There is a lot of really nice plugins. For example, Intact Solutions is an FEA simulation for meshes. It's implicit analysis. You can know more about them in their website. So they are really nice if you are going to do something simple and at the same time complex. So you can do certain type of definitions. They have thermal analysis, static analysis. They have certain type of boundary conditions, certain type of materials. It's always linear. So you don't have the part of non-linear and so on, but it may be helped to inform the earliest stages of design. Yeah.
Yeah, exactly. And that also answers the question from Miguel Escalon that asked about what does it mean that you develop your own tools? Is that exactly that what you said, that you develop your own clusters with Grasshopper and other programming tools? Let me check. The next one is from Marwan Fami. Do you use motion tracker for the shoe design in order to simulate the motion?
There are different ways to do it. It depends on what you have available. You can use motion tracking, but then you need to to use that in a specific way into your simulation. So if you're going to use motion tracking, you need to set up everything in the way that actually makes sense. So you need to do all the inverse kinematics in order to do that. And if not, you need to understand what type of information is the one available and how can we actually use it in order to create this type of simulations.
Okay, thanks. And Aaron is asking, how did you make the meshes for the track cleat? Not sure what's the track cleat, but
How do you make? Yes, we use Grasshopper. We use the triangulate mesh and different kind of mesh softwares, mesh algorithms that we have inside Grasshopper. Then inside LSDyna, we use their API in order to convert those in a FEA mesh, so we can do a remesh directly on LSP post.
okay. And the next one again from Miguel. He asked more about the company and about how did you start it and how did you come about your clients?
This is really interesting. Actually, we started because we saw that it's difficult to. I mean, there was the lack of creating a structure in terms of computational design for product or for consumer products. So we wanted to create something, a company that actually can start offering like a more complete solutions. So that's why we started to do Moonrabbit. It was also based on the experience that I built in the last 10 years. And I saw the opportunity to identify exactly, okay, everything kind of converts in computational design. We can specialize in this specific sector of computational design. So we want to reach the people in order to not be afraid of using new technologies and new trends. So the part of the clients is actually for us sometimes the hardest part, because you need to change the mindset from traditional methods into new methods. So that's why we are trying to collaborate to create new case studies and so on in order to actually build kind of a community behind computational design for consumer products.
Okay, thank you. And Robert Faulkner is the next question. What are you working on now, and what technologies for fabrication are you most excited about in relation to computational design?
I mean, I like FDM because I think it's the hardest one. But we are trying to we are trying to learn different type of technologies, SLA, SLS, robotic hand, and different approaches. Now we are specialized in FDM because I think it's a cheap technology that we can achieve really good results. So that's why also we did the project of moon landing. So we wanted to use a 300, our objective was how can we use a printed of 300 euros TPU material in order to produce a product that actually uses the function of footwear. No,
Mhm.
so we wanted to create something that has different stiffness levels. They have different insoles. How can we program it? How we need to program the material, the extrusion, the velocity, and so on, in order to create in one single shape a product that actually performs. So it's not about only like the manufacturing itself, is also about how can we use those technologies to create something that is really close to what we did. So that's why FDM so far is something that we are curious about it.
Thank you. Yes. I lost now the last question. Sorry. Uh, I think it's the one from David that I think he should contact you directly because he's studying computational design and he says if you may accept interns in Moonrabbit.
Yeah, you can send us an email and then we can talk about it.
Yeah, and the other one is if you think is there any real alternative to Rhino and Grasshopper in your area of activities?
Um, I mean, so far we haven't found one. I think there is a lot of different tools that actually can go in the same like overlap with Rhino and Grasshopper, of course. But the thing is like let's say the cost of those tools. So it depends of what you are doing, what's the cost, what's the budget involved. So you could use different tools, but also you need to see in terms of business what actually makes sense for what you're doing. So far for what we're trying to do is to demonstrate maybe we are spending a little bit more of time doing certain stuff, and but at the same time we are trying to develop in something that actually is a little bit more of open in a way. Yeah.
Yeah, thank you. And the next one from Ripu Melo. What's your next big collaboration? What's your
Okay. To,
project now?
2025, you will see it.
Okay, okay. We will need to organize a new
you need
webinar.
you need to wait. Yes, a bit.
Okay. And Jorge Tavares was asking that he heard that Rhino can be problematic for 3D printing. If you confirm that, and what precautions should be taken when modeling to avoid difficulties. I sent
uh,
him already a guide about how to prepare your models for 3D printing. But I think also with shrink wrap now in Rhino 8, it's much easier. Just because I think the problems could be just that the poly surface is not uh, closed or a mesh. And with shrink wrap, you can fix that to send it to an STL file.
yeah. So I think it depends also about the problem. So that you are trying to solve. So the Rhino, I think now Rhino 8 has a lot of tools that like shrink wrap that help to solve a lot of the difficulties in 3D printing. Yeah.
Yeah, because I was thinking what could be the problem, but I can find more than that. That if the object is not closed, it won't print. But yeah, I think that was the last one.
Cool.
Hope I didn't forget anything. So thank you again, Jesus. It was
Thank you,
great.
Guillermo, for the invitation.
You're really welcome. And we will see then the next projects.
Ciao,
Nice to see
ciao.
you. Bye bye. Thank you.